So, goal today is we are going to look at multiple object systems and solve for forces inside and outside the system, as well as system accelerations. So we're going to use our lab example where we've got the cart on the track and we've got the mass off the end on the string. And we have two goals here. We want to find the system acceleration and we want to find the tension in the string. Right? There are two ways to solve this, right? And we're going to look at both of them. They have kind of a fundamentally different starting point, right? And so we'll call this method one, method two. One is not necessarily better or worse than the other, but they will kind of work you through your solutions in a different order. So depending on what you need, one might be better than the other, right? So method one, right? This is the we'll call this solve as a system. And method one finds acceleration first and finds tension second. All right. So this method, we'll work this. This is something that we have talked about before, where this is how we did our lab, right? We set up our cart and masses as a system. And so our system here is both the cart and the hanging mass, right? So our system is this sum of these two objects. Right? We're going to treat these as sort of a unit, right? And they will move together because they're tied together. The challenge when you do a system solution is to figure out what is the net force on it. And this is where just a little bit of practice and familiarity comes in handy. So what is the net force on this system right here? This is one we should hopefully be familiar with. What's the net force on this car hanging system? And what about little m? Little m is not a force, little m is a mass, but we're close.
2m.
That's going to be our system mass. Go back to little m. How do we turn this into a force from gravity? And how do we do that? Okay, so multiply that by g, right? Which is 10. So your system net force is going to be the weight of the hanging mass, which in this case equals little m g, right? This is going to be little m g. And from here, we can just use Newton's second law on the entire system, right? And we can say, all right, acceleration equals net force over mass. And when we're doing this, we have to be careful about our variables, right? Because this is the system. This is the system. So then when we plug these in, we just get little mg over the sum of big M plus little m, and this is it, right? If you have numbers, you can put in numbers, but this is our general solution, right? This is our system acceleration, all right? There's our system acceleration. And this is a form that you need to be comfortable with all the big M, little m, m1, m2, something like that, right? Questions on this method? Hopefully this is a little bit familiar. If we are going to try to find the tension in the string, we need to look at one of objects. So to find the tension, we cannot find the tension by looking at the entire system, because the tension is inside the system. Right? The tension is within our two objects. So to find our tension, we want to look at just one of these. And it doesn't really matter which one we use, but I think this one will be a little bit easier to deal with. So if we draw just big M, all right, if we're going to do a little free body diagram for just M, then we want, so here we'll do this is solve for T. Right? So big M has its own weight, has normal force from the track, and it's being pulled horizontally by T. Right? So the net force on the relevant axis of acceleration here is just the tension. Right? So the reason we used the cart and not the hanging mass here is because the cart only has one force on the axis of acceleration, so the net force is just equal to T. If we were going to do the hanging block, the relevant axis of acceleration is vertical, and so we would need to look at two vertical forces to get the net force. It would be its weight down minus the tension up, and so we'd have to do a little bit more math, whereas this, T is simply equal to the net force because there's no other horizontal forces. Right? So we can say that acceleration equals net force over M. And so we're running this again, but this time we're running it for just the cart. All right, we're not running it for the system, we're running it for just the cart. And so all we need to do is plug in our acceleration of the cart. We already have this really messy combination, so we can reuse this. So acceleration is just mg over big M plus little m equals net force of T divided by big M. All right? And so to get your expression for T, we can solve this, multiply big M by both sides. Right, so just do a little times M, that cancels out, and we get T equals big M times little m times G all over M plus N. Okay, this is solution method number 1. Take a second to digest. Let me know if you have any questions. You can cut. One of you, can you cut the...
So in that equation.
The other method that we can use to solve these, we'll call this method 2. Right, this should get us to the same final result. This method involves using the two objects separately. Right, so instead of setting them up as a system, we're going to consider both objects separately. There's going to be a little bit of overlap here. So this will solve as two objects, and this method will end up solving for usually the tension first and then the acceleration second. Right. So neither method is better or worse than the other. It all depends on context. Depending on what your question is asking, if you need to find a tension, then it might be easier to just do it this way. Right? If you just need to find an acceleration, it would probably be easier to do it this way. Or you might look at one of these and say, this makes a lot of sense to me, I'll do this. The other one, I don't know about that. Right? So, but both of these are good solutions here. So for method 2, we want to consider both of these separate objects, and so let's draw our free body diagram for both. Right? So we're draw FBD for each object. And so we can reuse what we had before. Right, here's our cart. We know our cart track and has a T over here. And then our other hanging mass has T is up and it has mg, little mg down. Alright, so we got two free body diagrams, and what we're going to do here is write Newton's second law for both of them, and then we're going to use some substitution to solve for our variables. Right? We're going to end up with two unknowns in this. We have unknown acceleration and an unknown tension, but we have two objects. We can write two equations, and then we can solve them together. So that's kind of our mathematical process. So we're going to write acceleration equals net force over m for both of them. All right, so luckily we're just going to kind of reuse what we had over there. For our cart, acceleration is equal to tension divided by cart mass. All right, so our net force is our tension, and our mass is just the mass of the cart. That's big N. And we're going to write the same thing, same equation for our hanging mass. For the hanging mass, our net force is going to be the difference between the weight and the tension. And important here that we are consistent with our signs. Positive acceleration is down, right? This is accelerating down. And so we want to do our down minus up here. And so we're going to go mg minus t is our net force, right? It's the difference between these two over little m. George?
So when you add and get rid of the g, all it's doing is changing it from kilograms to newtons, right?
Right, the g is going to give you a weight from a mass. So here we have unknown acceleration, unknown tension, and we're gonna solve for our tension. So we want to basically, both of these expressions equal acceleration. We can set these equal to each other, and then we can solve for t. Right? So then set, use substitution, and here's then t over big M equals mg minus t over little m. And we are going to have to do a little bit of algebra on this to solve this. So let's say that this is going to be Tm. I'm just cross multiplying these. Alright, so this is a cross multiply. Then we want to collect all of our t terms. Alright, so just add this to both sides to collect all of our t's on the same side. Factor out the t and divide. So let's factor out our t. So this ends up being, this is t, m plus m over here. And so then our final thing is t, m, and g divided by n plus m. So this is exactly the same as we had last time. And it should be, right? This is the same as we had last time. The difference is that again, depending on what your question is asking, if you just need to find the tension, then maybe this is easier because you get it first as opposed to having to find acceleration first. But ultimately it kind of is what you are more comfortable with. From here, in order to get your acceleration, just take your tension, plug it back into one of your equations. I would recommend this one because this one is really easy, and I'm running out of room on the board here. Plug T into equation to find acceleration. So if you put this expression for T into this equation right here, then your big M's will just cancel out and we have an expression for A, right? So this is not too bad. So A is equal to big M, M, E over M plus N over big M. So A equals mg. Alright.
So it doesn't matter which one you plug it into?
Does not matter which one. This one will be really simple to simplify. Like you just literally cancel out one thing and you're done. This one would be a lot more work to simplify, and I would not recommend that unless you just feel like doing some extra algebra because that makes you happy. Okay, questions on this process? Should we try a couple of these? Well, we'll try one of these. I want to see how we can do on this. So on the fun sheet that I gave you.
Didn't say fun shit.
Oh, I forgot to write the word fun on this sheet. I forgot. So what we just did here is actually the solution for set 2, number 1. All right, this is set 2, number 1. So I think what we should do here is we should do, let's just do number 1. Should we do number 1 or should we do set 2, number 2? We're gonna take a real quick vote. Should we do set 1, number 1, or should we do set 2, number 2?
Set one, number one.
Alright, so we're gonna do a real quick vote. Give me either a 1 or a 2. Set 1, 1, or set 2, 2. Real quick vote. So we've got, let's see, hold on. We have,
Which one is easier? 2.
that's up to you. So we have a vote, is that a 1 vote?
Yeah.
A 1, let's see, so we have 1 for 1, 2 for 1.
I'm undecided.
Alright, 2 votes for number 1 and lots of votes for number 2. Alright, so let's try, let's take a minute, let's see what we can do with set 2, number 2. It occurs to me that I may not have, there might not be enough space on this, so if you want to write these out on your notebook, go for it. So our goal here is to find acceleration and the tension in both strings. Yes. Alright, acceleration and the tension in both strings. You can cut it.